Today we are going to be doing transformations of sine and cosine. I actually put thought into these first slides I pick all the time. Not that you can tell, but this one is supposed to be showing waves transforming. That's what's going on here. Example 1, state the transformations that were applied to the parent functions. Here's the parent function, and then we're going to sketch one cycle. So here's our parent function for cosine, which we've talked about already. The important points to graph on it are the maxes. This is one cycle right here, one period. So the maximum values are important, the minimum value, and the intercepts with the x-axis. Those are the ones we focus on graphing right here. With all of these transformations, we're going to sketch a new graph. But first, we have to divide the k value out of the brackets. You can change theta to an x if you want to. That sometimes makes it easier to see how to isolate x. So our k value is a 1/2, and now our x or our theta, our independent variable, is isolated there. So now that that's done, we can state the transformations. And transformations can be done from left to right. That will follow a proper order of transformations. So we'll start with the first one here, -3. That's an a value. A value of -3 means a vertical reflection. That's a negative. And then we have a stretch times 3. So imagine this graph here flipped over. So now it's like this, right? It's flipped over and stretched by a factor of 3. So its amplitude would be a 3. So that's what that first transformation does. The next one is the k value of a 1/2. That's going to give you a horizontal stretch. So look at that red graph again there of cos. Imagine pulling it by a factor of 2. So our period is going to change. Our period in the parent function graph right here is what we would have said before, 360 degrees, but it's now 2 pi. But now we're stretching it, we're pulling it out. The next transformation is the d value of pi over 2. And we're used to having d values of +7 or something, not anything with a pi. But pi is part of the d value here. So it's a horizontal translation. That whole graph is going to shift pi over 2 units to the right. And the last one is the c value. That's supposed to be a 2 right there, not a 0. C value is 2. That's a vertical translation 2 units up. So there's the transformations that were applied. But now we have to graph it. So the third step is to graph one cycle. We're going to use a coordinate chart. So we're going to use a chart, and this is one way to do it. There are many ways to graph, and I'm just reviewing one of the methods here. But this chart is good because it shows how each coordinate is transformed, but we are going to speed it up a bit by doing 2 steps at once. So first of all, we're going to start with our cos parent graph. That's this one right here. So I want to list some coordinates down here that are just in the cos parent graph. So you can look at the graph, or hopefully you have a few memorized. You really only need the first one memorized, 0, 1. And then you know that every 90 degrees or every pi over 2, something important is happening. Either it's an intercept, a max, or a min. So every pi over 2, we have something happening. So there's the rest of them. Those are the 5 important coordinates on the cos graph. Now our next step, k and a, are multiplication and division, and they have to be done before addition and subtraction. That's why I'm doing them here. But why do I have it listed k and then a over here? I talked about a first and then k. That's because k affects the x value, a affects the y value. So when I put in my new coordinate here, I want to just line it up. It's a little bit easier for me to look at if it's lined up. So a k value of 1/2 means I'm actually taking all of the x coordinates and I'm going to multiply them all by 2, because really what you're doing is you're taking your x values and you're dividing them by k, right? So we are taking x, we're dividing it by 1/2, which is x times 2. So that's what I'm going to do with all my x's. So if I just start off with that here, I'm going to open a bracket. If I had a 0, 0 times 2 is 0. My next one, pi over 2 times 2 is pi. So I'm just doing one part of the coordinate here. Now I'm doing pi times 2. That's going to get stretched out to 2 pi. So look up to the graph for a second here. Let's just talk about that one. this coordinate here is what I'm working on right now, pi negative 1. So that's going to be stretched out to 2 pi. That's what my k value is doing. I'm taking all these and I'm stretching them out. That's my first step, is to take all these points and just give them a horizontal stretch. Okay, back to the chart. 3 pi over 2 times 2 is going to be just 3 pi. And 2 pi times 2 is 4 pi. So there's all of my k values. Now I'm going to go up to the a value. A value is a negative 3. So I'm going to take all of my y coordinates that are there and I'm going to multiply them by negative 3. So this is how I'm doing 2 steps in one here. So 0, 1 is going to go to 0, negative 3. Pi over 2, 0. So pi over 2, 0 is going to be transformed with these two transformations. It's going to land at pi and 0. So that's where it's going to land. Pi negative 1 is going to land at 2 pi 3. 3 pi over 2 and 0 is going to be pushed to 3 pi, and that's going to stay at 0. And 2 pi 1 is going to go to 4 pi negative 3. So those are our first two transformations, and the reason we did those first is because we're multiplying or dividing. We're taking our x and our a and our k and our a's, and we are multiplying or dividing the x and y values. So multiplication and division have to be done before addition and subtraction. The d and c values are adding and subtracting. They're shifting everything to the left or right or up and down. That's an addition or subtraction, so we do that last. So I'll do that here in the last column. So I'm going to take all of my x's, and I'm going to add pi over 2 to them. And at the same time, I'm going to take all of my y's, and I'm going to add 2 to those. So 0 plus pi over 2 goes to pi over 2, and negative 3 plus 2 is negative 1. So this coordinate that we had originally, 0, negative 1, and I'm going to go up to the graph on the top right here. 0, 1, sorry. 0, 1 was right here. That's now been transformed to pi over 2, negative 1. So that's going to be down here now, but we'll graph it in a minute. So that's the result of all the transformations happening to it that we talked about in the pink with the arrows. Those are all the transformations. So I want you to press pause, and I want you to finish the rest of the coordinates. Actually, we'll do one more just because I want to work with the fractions with you a bit. Pi, I look at this value of pi here. I want to add pi over 2. So ignore the pi and think of it as a 1, and then you're adding on a 1 over 2. Think of it like that. And that 1 plus 1/2 is 1.5, or 3 over 2, but you've got to put the pi in there, so it's 3 pi over 2, comma 2. And since our x-axis grid is always in fractions, we don't want to convert these to decimals. So try the last 3 coordinates yourself. Okay, now I did 2 steps. I did 2 and 1 in each column here, and you could have drawn a line right down here and just done the k first, and then the a, and then the column down here, and you could have done the d and the c. So when you're doing this chart method, you can certainly break it up even further and just do one step at a time, but this just makes it a little bit faster. So this isn't a method that you have to use, and if this method confused you because you don't like setting it up like this, then don't do it. We have others. We have a little coordinate equation method. We have using transformations. We have max-mins. We have all kinds of ways to do it. So if this method didn't work for you, that's fine, but you should, whatever method you use, you should have these coordinates. So here's the grid, and the benefit again of this one is it takes us through each coordinate and tells us how it's moving, multiplying by 2, or it's telling us what's going on here. So we've got our grid, and now we're going to plot all of our points on the graph. So again, press pause. I'm going to press pause here, and then when you come back, you'll see all the dots on there. So there's the dots, and it's really tempting to just draw a straight kind of V shape like this, right? But that is not a wave. So I'm going to start at the top point, a max, and I'm going to just connect. I'm just going to go to the right and left to each point here. So I'm just going to curve down here, whoops, and curve down here. That always disappears. Okay. So I'm trying to make almost like a parabola or like it's concave down shape. Now I go to those midpoints, those equation of the axis points along the two, and I'm going to curve up from the minimum. I'm curving up to that here. So make sure you are drawing waves and you're not drawing straight, and nothing should be straight here. It's very important, and we get into this when we talk about the rates of change of these functions, that they are curved and not straight, not constant. And I'll put some arrows at the end here. We only had to draw one cycle, but of course this continues on. And if you look at the scale along the x, this was easy for us because I already gave you the whole grid laid out, right? But 2 pi, here's 2 pi on the parent function, here's 2 pi here. I had to more than double that because I knew I was going to stretch it out by a factor of 2. I knew it was going to stretch out by a factor of 2, and I knew it was going to shift right pi over 2 units. So I had to get a larger x scale on there. You can also look at your final coordinates and they will tell you, they will give you an idea of what to use for your scale. 9 pi over 2, so ignore the pi. 9 over 2, that's greater than 4, so you know you have to go to 4.5 or to 5, like I did here, to make sure you cover it all. The last thing, to check your answer, you pick a coordinate from the graph. So I might take this one right here. I could take any point, take the first one if you want, pi over 2, -1, and you sub it into the original equation. So the original equation before I made any changes to it. So let me just find a spot up here to do that. I'm going to write the original equation. Well, this is my original equation here. So if I sub in, I'm going to use the first one we got, pi over 2 and -1. This is an x, this is a y. So on the, looking back at the equation in the black box here, the y, that would be the -1. So I'm going to sub in the x. Now remember x and theta, we sometimes use those interchangeably. So I'm going to put my x value there. So my left side has got to be a -1. My right side of the equation is going to be -3 times cos. And now subbing in, this gets a little weird here. My theta is pi over 2, and then that's got to go over 2 minus pi over 4 plus 2. So pi over 2 over 2, pi over 2 divided by 2 is pi over 2 divided by 1/2, divided by 2 over 1, which is pi over 2 times 1/2, so that's pi over 4. So I'm going to change that to -3 times cos of pi over 4 minus pi over 4, that's nice. That's going to be a nice easy bracket there, plus 2. So -3 cos pi over 4 minus pi over 4, of course, is 0 plus 2. Follow the order of operations. Do not do 0 plus 2 first. That's not how we order of operations. We don't do addition first. We're going to have to do this function first. Cos of 0. What is cos of 0? Cos of 0, here's 0, 1. Cos of 0 is 1. So I'm getting -3 times 1 plus 2, which is, of course, -1. So that's a good way to check to make sure that your coordinate you got on your graph is correct by going up to the original equation. Next question. Read that to yourself, and when you think you're ready, let's work on the question. Okay, ready? What have we got here? So we're starting with the parent function of sine, and we're given a whole bunch of information about it. We have to write the equation of the resulting graph. The first thing we have is it's transformed by vertically compressing, that's an A value, vertically compressing by a factor of 1/3, and reflecting in the y-axis. Reflecting in the y-axis, that's not the A value, that's the K value. So let's write some of this down here. We're going to have an A value of 1/3. We're going to have a K value, so we've got horizontally compressing by a factor of 1/3, and we've got the reflection there. So the reflection means k is going to be negative. It's reflecting in the y-axis. Remember y-axis, so always go to your parabola or something. If I was reflecting in the y-axis, that would be flipping it around this way. Okay, so we are looking at horizontally compressing by a factor of 1/3. That part's always confusing. If you're compressing it by a factor of 1/3, it means you're squeezing it in to occupy 1/3 of the space between the y-axis and its original function that it was. So that means our k value is actually a -3, not a 1/3. It's the opposite of what you think it's going to be. The next one is D. Change colors. D. Horizontally translating at pi8 units to the left. So again, if it's going pi/8 units to the left, that means it's a negative, and it's pi/8. But in our equation, it's going to be the opposite. It's going to be a positive. I'll go over that in a second. And then we've got the last piece. We've got vertically translating 23 units down. That is, of course, the C value, so it's going down 23 units. So how do we put this all together? The equation of, without any transformations, is y equals the A value is here, and then you use either sine or cos times, in this case we're using sine. Then we have a square bracket, our k value comes next, and then x or theta, or whatever your independent variable is, I'll use x, minus d, and then plus c. So notice the format itself has a negative right here. So when we put in the negative pi/8 for d, it's going to become a positive. So our answer is going to be y equals 1/3 times sine of our k values in -3, our x, we're using x, and then plus pi/8, close both brackets, minus 23. So that's all there is to that question. It's a question that was actually in your textbook, but students sometimes get confused because of the 1/3 and the 3 and all that, so I wanted to go over that one for you myself. Example 3 is our last one. So read that one to yourself, press pause, and then come back. All right, lots of information here. Let's start at the beginning. A weight is supported by a spring. You should be able to visualize that. You should visualize a spring, and a weight is bouncing up and down on the end of a spring. The weight rests 50 centimeters above a tabletop. It rests 50 centimeters above a tabletop. That means your C value is 50. That's your equation of the axis. That's your rest point there. That's where it's resting. So it's not being shaken or lifted or dropped or anything right now. It's just resting at 50. Then the weight is pulled down 25 centimeters from here, right? So it was resting at 50. It's pulled down 25 centimeters, and then it's released at time 0. So imagine you're pulling it down and you're waiting to start your stopwatch. What that means is you've got your initial position. Your initial position is, your independent is z, and this 0 in this case is going to be time, and 25, because it's not because this number is a 25, but because 50 minus 25 is 25. What's next? This creates a periodic up and down motion. So we're assuming it's a perfect world, and it's just going to keep, the spring is going to keep coming up and down, up and down, up and down at the same rate, and it's not going to start getting lower or lower. It's just going to stay with the same amplitude and everything. So the weight reaches a height of 25 centimeters above the rest position. So remember where the rest position was here? So the maximum height it's getting to is 25 centimeters above that. So our maximum is 25 plus C, which is our 50. Next piece of information, it takes 1.6 seconds for the weight to return to the low position each time. So to get down to the bottom each time is 1.6 seconds. So 1.6 is our period. And we have to sketch a graph of the height of the weight, that's where height of the weight, above the tabletop against time for 4 seconds. And then we're going to write an equation. So we've got a lot to do here. Let's come up with some information. The max and the min are really important always in any kind of trigonometry question here. So we need that for our range and for our y-axis scale. So first of all, and we'll use to calculate the max and the min. Let's get our max and min here. I think we already have the max on the side. We already talked about the max. So our max is 75. Put that here, our max. Our max is 75. And what about the min? What's the minimum value? So that's 25, remember, because it goes down 25 below 50. So our minimum is 25. So now we can get our amplitude. Our amplitude, there's absolute value signs there because amplitude is always positive. So when we come up with the equation, we can make the a value negative, certainly, but right now we're just going to come up with the amplitude as a positive value. So what have we got for our amplitude? Our maximum is 75. Our minimum is 25. Divide that by 2. So 75 minus 25 is 50. 50 over 2 is 25. There's our amplitude. Next is the C value. It's almost the same formula, but this time it's the max plus the min divided by 2. So 75 and 25 is 100. 100 divided by 2 is 50. And we already knew that. We already had that way up here at the top, right? We already knew that. We didn't have to calculate it. And the K value. So we know the period is 1.6, but that's not the K value. The K value also has got to be positive. So our K value is 2 pi divided by our period. And our period is 1.6. We got a problem here with decimals and fractions. That's not good. So we're going to simplify this. 2 pi, and I'm going to change that 1.6. Instead of divided by 1.6, I'm going to make that a fraction. 1.6 is 16 over 10. So that gives me 2 pi. I'm going to invert and multiply. That, oops, sorry, that should be times 10 over 16. And we're going to leave the pi as a pi. We're not going to change it to a decimal, but we can do some reducing of all these fractions here, and we get 5 pi over 4. So you can do the math on that yourself if you don't know where that came from. To determine D, we first, let me erase this here. To determine D, we first need to decide if we're using sine or cosine. So we've got here, we figured out our A, C, and K. Now we need the D value. So it's always easiest when you read the question if you can figure out the initial position. So our initial position is 0, 25. Let's go over to the graph here. We're going to put some of these values on the graph. I've got my max and min. I've got my range. So I'm going to, I think I can count by 5s here. This is my y-axis is my height, and we're measuring that in centimeters. So at the very bottom, 0, that's the tabletop. So we're going to count by 5s, 5, 10, 15, 20, yeah, count by 5s there. So there's 25. And I think I can fit the rest on. Yes, it all fits. Now across the bottom, my independent axis is time. And we're going to measure time in seconds. Actually, I'm going to move that down below. I think it'll be in the way there. Okay, and I'm getting all these units from the question. There's seconds right there, and then centimeters it's all in the question. So that's where that comes from. Now we have to graph it for 4 seconds. So I've been given my domain of 4 seconds there. So I'm not going to go 1, 2, 3, 4 and squeeze it all in. That's ridiculous. I'm going to spread it out. So I think I'm going to count by, let's see, I've got numbers here, 5. So I think I'm going to count by 0.2. Right, so I certainly could have spread it out more than that, but that's okay. I don't want to crowd it in any more than that. Let's get some coordinates on here. We've got our initial position, of 0, 25. So 0, 25, there's our first coordinate at 0, 25. Now, trig graphs are great because they're so symmetrical. I have one point and that is all I need. I can get a whole series of waves from one point because I know so much in the question. I know that every 1.6 seconds the weight is back at the low position. So I'm going to go to 1.6. I'm going to put another dot there. 2, 4, 6. So we're right back at the low position of 25 centimeters right here. And that's going to happen again in another. So I'll write the coordinate for you here. This is 1.6, 25. And that's going to happen again in another 1.6 seconds. So that would take us to 3.2. So I love the symmetry of the trigonometry. It's once you know a little bit, you know a lot. So 3.2 and 25. And this keeps going on. Every 1.6 seconds, everything's repeating. Halfway between the minimums, always is the maximum. So you know our maximum is 75. At what time will we be at 75? Well, that's halfway between 0 seconds and 1.6 seconds, so that's 0.8 seconds. So at 0.8 seconds, I'm going to put a dot up there at 75. So this coordinate is 0.875. So that's my first maximum. When am I going to get another maximum? I'm going to get another maximum halfway between these two, or in 1.6 seconds from my first maximum, I'll have another maximum. That's going to be at 2.4. So 2.4, I think, is here. So we've got 2.4 and 75. And my next one, I'm going to have another maximum that's going to fit on there, another 1.6. That's right to the edge of what I have to graph, which is 4 seconds. So right here at 4 seconds, I have another one. Okay, the other important points of any trigonometric function, sinusoidal function, are what they're called the points of inflection. They're the equation of the axis. So my equation of the axis is, my C value is 50. So right across here, if I drew a line, that would be my halfway line. That would be my equation of the axis at 50. So it's important to know when my graph is hitting the equation of the axis. And of course, beautifully, it hits in between, halfway between a max and a min. So between 0 seconds and 0.8 seconds, halfway there, halfway between 0 and 0.8 seconds, I'm going to be on my equation of the axis. So that means I'm at 0.4 seconds, I'm going to be at 50. And that one occurs not just every period, but every half period, because we're going up and down in one cycle. So I'm going to have another one over here and so on. So these are occurring every half period, not just every period, because if you look here, one wave hits the equation of the axis twice, not just once. So it's not just every period, we have that every half period. So continue putting your dots on and graph your wave. So we didn't have to do the graph yet, but I jumped ahead to that because remember I stopped here on to determine D. So we still need to find the D value, and sometimes it's easier to see that when you're looking at a graph. When your graph on the y-axis is at a max or a min, in this case a min, then it's easiest to use cosine with a negative a value, because the parent graph for cos starts at a max. We want this graph to start at a min on the y-axis, so we're going to have to give it a vertical reflection. So my a value, I'm going to make it negative. You don't have to. That's one way to do it. Another way to do it is to leave, so let me do it, I'll do it the second way first. Let me start with the formula that we have to sub into. H at t, so we can have a negative a value, that's negative 25 times cos, and our k value is 5 pi over 4, And then t minus d, in this case we're having a d value of 0, so this would just be a t here, plus c, and our c is a 50. That's one equation. Now let's do another equation. The next equation I'm going to do is if we don't take a negative a value with cos. So the height as a function of time is equal to an a value of 25. But then if I don't have a negative a value, I'm going to have a d value. So how do I find that d value? The rest of it's all the same. 5 pi over 4 t, I'm going to leave this blank, plus 50. Okay, let's look at the graph. My d value, my parent graph, remember, let me just draw a parent graph underneath here. Parent graph of cosine is like this. Not really like that, but this is the important part right here. The maximum, the first maximum is here. So if I'm not taking a negative a value, what I'm looking for is where is my first maximum now? Where did this first maximum get pushed to? Because it was at 0. That's a d value of 0, my maximum there. Here my first maximum is at 0.8 seconds. So that means my d value would be 0.8. That would be me saying I've taken this graph, I've pushed it over to the right 0.8 units, and then I've already taken into account everything else. So to state the equation that way, I'm doing t minus, because there's a minus in the equation, remember, t minus 0.8. Now we have fractions and decimals here, which is not okay, so I'm going to convert that 0.8 to a fraction. So I've got my equation here with a 4/5. I also added this in. D is the x value of the first maximum. I put first in quotations because I could have used this maximum here if I wanted to, or this maximum. I can use any maximum for the d value because the parent graph, the first maximum is at 0, but we have an infinite number of equivalent ways of writing the same expression. So I picked the first maximum there, which was 0.8, which translates to 4/5. That's the end of your lesson on transforming sine and cosine using radians.